All right, experiment 23 is the kinetics experiment with concentrations. So there's a lot to cover. I'm going to talk quickly, assuming that this is a video. You can pause it and you can rewind it, or you can put me at like half speed so I go slower. So let's get started. Basically, in this experiment, you were doing a reaction that involved acetone, which is written CH3, COCH3, just so you know. H plus in the form of hydrochloric acid, HCl, and the iodine, I2 here. And we were putting them together, and we wanted to see how much each of them is affecting the rate. For example, we don't know that this is true or not, but let's just say for a second that acetone can run really fast, super fast, and this one can only run medium, and this one is walking with a cane and is very slow. If we have a race and we're looking at the rate that these are going, it doesn't really matter if they're on a team that this guy's fast and this guy's medium, because if all of them need to cross the finish line, he'll cross first, he'll cross second, this one will cross third, but because they have to cross as a team, because the reaction is working together, he's like the weakest link, he's the slowest, and they can only go as fast as the slowest one is going. So we're trying to see if we double something, does that double the rate or not? Because if we double the concentration, like if we double the concentration of the acetone, it doesn't really matter because he's already the fastest guy. Maybe, it's just an example. So here's our rate, equation. Rate equals K times acetone raised to the M power. We don't know what M is. We're trying to find it. I2 raised to the N power. We don't know what N is. And H plus raised to the P power. Now, keep in mind that these two flipped here, and that's okay. So, we do know that the P power is actually 0. It says that in the lab report. It says that I2 is 0 order. And we're trying to figure out what these numbers are for the exponents, and we're trying to confirm that 0 is the case. All right, backing up. So we did 4 experiments, or 4 experiments. 1, 2, 3, 4. I did this back in 2012. So we didn't do experiment 1 with 2 trials. We just did experiment 1 and knocked it out. You should have 2 trials and you can average your data together. I will just be doing my 1. So what we did is experiment 1 is kind of the baseline. We put 10 milliliters of acetone in, 10 milliliters of HCl, 10 milliliters of everything, and 20 mils of distilled water. Now it's a lot of distilled water, but it's distilled water, so it's not doing anything. So this is just baseline, 10, 10, 10. Now what if then I have 10, 10, but I double my concentration there for the iodine? How is this going to affect the rate? That's what we're trying to figure out. What if we keep this at 10, this at 10, and we double... Daisy, it's okay. Alright, and we double this. Oh my goodness, it's okay. Stop barking. There are people with headphones listening. Oh, yeah, I know. Alright, so we're doubling this one, and you get the idea that we're doubling something each time. Now, water is going to go down to 10, but that's mostly just because we want to have 50 milliliters each time, and 10 plus 10 plus 10 plus 20 is 50 milliliters, and these ones equal 50 milliliters. It's 50 milliliters each time, which makes calculations really simple. Alright, now, we know that we added these milliliters, but we have to take into account that this is 4 molar acetone, 1 molar HCl, and 0.0050 molar of the iodine. So, when we do that, let's do a M1 V1 equals M2 V2 calculation and find big M, or molarity, which is moles over liters. So I have 10 milliliters of acetone, and so that's like V1, and then M1 is my concentration of it, so that's 4 molar, and then I need M2, so I'm going to be solving for that. V2 is the total volume of the solution, which was the 50 milliliters that we get when we add 10 plus 10 plus 10 plus 20. Enter. This is my concentration of the acetone in experiment 1. Now, I can do that for all the cells, or I can kind of cheat a little bit, grab the corner and drag it down so I don't have to calculate it every time. So, in experiment 1, 0.8, 0.8, 0.8, and now it doubles, which makes sense because up here we added twice as much of it. Moving on. Equals 10 milliliters times the concentration is 1 divided by total volume 50 milliliters. Drag, double check that this one is double the rest because it is up here. Good to go. Next, 10 milliliters times concentration. Be careful with your zeros. 0.0050 divided by 50 milliliters. Drag and check that is more than the rest, and it is. Okay, now let's confirm first that the order, the exponent of I2, which is n, let's confirm that that's 0. So, baseline is, well, actually, can't do that yet. Sorry, got ahead of myself. Backing it up. Beep, beep, beep. Pull out your lab data, and you need to put in how much time it took, because that's the whole point. And when I did it, got that this took 232 seconds for the first one, 459 for the next one, 115 seconds for the third one, and 105 for that one. Now the rate is going to be the change in concentration over seconds. So let's make that happen. Change in concentration for I2, which is what we're trying to find for this first part. Here's the concentration. Here's, oops, sorry. Here it is, big M, see? Molarity. There's my concentration. Divided by seconds, which is that. So again, I'll do it one more time. Delete equals M divided by S. Enter. There's my value. Same as before, I can grab this, and in my little cheater way, it will do it for me. It'll take this, divide it by that, enter, I've got my rate. Now I can move back down here and say, all right, let's compare the experiment that iodine was doubled in, which is experiment 2, and let's compare that to my baseline, which is experiment 1. In experiment 2, I doubled the iodine, but I did not observe a change in rate. Those numbers are very similar, 4.3, 4.4, they're the same. So I did not see a change in rate even when I doubled the iodine. This means that it is indeed a zero-order reaction. The next one that we want to compare then is the, let's do the hydrogen. Sorry, I'm still filming. The next one we want to do is the hydrogen. So we doubled that in experiment 3. So comparing experiment 3 to the baseline means, here's baseline, experiment 3. So when we doubled the H+, we ended up going from 4.3 to 8.7. Mental math is telling me that that doubled as well. If we doubled this and the response was double, that means that we have an exponent of 1. Now if we doubled it and the rate was quadrupled, then we'd know it was 2. But since this doubled and this doubled, it's just 1. And last, for the acetone, we're going to be comparing the rates for experiment 4 compared to baseline 1. From 1 to 4, acetone was doubled, and then the rate from those was also about doubled. If you calculate it out, let's do it. This divided by this. It's 2.2 instead of 2.0, but that's close enough to say that this doubled and this doubled. So that means exponent of 1. Now the last thing we got to do is plug all this in. So I'm trying to find K. I don't know what K is, but I do know what the rate is. I know what the concentration of acetone is. I just figured out that M was 1. I2 concentration, I have everything, I just don't have K. So I'm going to try and get K all by itself, and I would suggest doing that on a piece of paper, but the Excel calculation is going to be just taking the rate, and I'm going to do it for experiment 1 first. So rate divided by the concentration of, where is it at? Of acetone to the first power multiplied by HCl also to the first power. You can see first power. And now I could include the iodine and say this to the 0 power. That works, or you can just realize that anything to the 0 power is 1 and not include it, but I did it for thoroughness. So there is the value of K. I can drag through Excel, and then I think maybe in your lab report it wants you to find the average of K, and you would do that by saying equals, spell the word average, put a parentheses, grab that, hit enter, and it calculates it for you.